Okay, I want to show you an example of how we can use linear approximation. And this question is coming from a little bit of a different angle in terms of it doesn't just say use linear approximation to approximate a value on a function, and they give you the function, and then you kind of are directed towards write the equation of a tangent line. So this one we have to be a little creative with. But I want you to join me in just starting to think about like radical 37, if I were to ask you to give me an estimate of what it would be. And I'm hoping that you're saying something like a little bit more than 6. And where am I getting that from? Well, square root of 36 is exactly 6. So it's a little bit more than square root of 36. So I don't know, 6.1, 6.2, maybe less than 6.1. Beyond that, I'm kind of stuck. So I literally am just guessing. So here's where some calculus could help me out. If I could write the equation of a tangent line, so I'm going to turn this into the question. Let f of x equal radical x. There's the function that I wasn't given. And write the equation of the tangent line at x equals 36. Then I'm going to evaluate the equation, or sorry, the value on that line at x equals 37. That's going to be close to the value on the function. So if you're a visual person, let's actually picture square root of x. And then let's picture a tangent line. So I'm just going to pick this value as my 36. And actually with this one, if I just kind of draw that in, the line actually does look like it pretty much is coinciding with the curve. We know it's not exact. But if I go slightly beyond 36, so I go to 37, the value on the line, or sorry, on the curve, and the value on the line are going to be almost right on top of each other. So that's going to give me a pretty close approximation. And this is a great example of like, okay, we can do a lot of things, and we can obviously do this with our calculator. But some of the ones that I've shown you, the math with the function actually isn't bad. And what I like about this is I actually cannot figure out, without my calculator, I do not know how to do the square root of 37. So that was something that people used to do before calculators, and I believe it was called the slide rule. And we don't learn that these days, and I've never learned how to do that. So I really don't know, without a calculator, I do not know how to get that beyond what I just kind of did as my basic estimation. So I'm going to work through the math here. So if f of x equals radical x, f prime of x equals 1 over 2 radical x, using my power rule and thinking of that as x to the 1/2, and therefore f prime of 36 is 1/12. I also need to know just what f of 36 is. And that's radical 36, which is 6. So this point here is my 36 comma 6. That makes this 6 on my y-axis. And that's my point of tangency. And a good place for us to kind of pick out, like, why did I, because remember, I came up with this line right here of what I was going to do. Why did I choose x equals 36? Well, because that's the closest place that I know the value to have an actual point to work with. And it's going to be the best estimate, since my tangent line is only a good approximation for within a range, both less than and greater than that value. So if I had used, for instance, x equals 25, sure, I could make an equation of a tangent line at that point, but that wouldn't be as good of an estimation. So if I put this together, now here's where I'm going to go back to what we were looking at, and I could just start with my point slope formula. But just to kind of go through this, so let's start with that. Actually, I'll use the L of x notation. So f of x, or f of a for some specific value, because our tangent line is always at a point, plus f prime of a times x minus a. And then my a is 36. So substituting that in, now I've got a 36 in here. 36 and 36. So let's rewrite one more time. F of 36 is 6. So y value, f prime of 36 is my 1/12. And I've still got my x minus 36. So here's my linear approximation. That is that equation of the tangent line. Now I could plug in any values I wanted. And if you want to have some fun with this, try plugging in something like 20. And I don't think that's going to be a very good approximation because look, my curve and my line are getting decently far away. So there's a space there, and therefore they're not going to be a great approximation. But I'm going real close, just above it. And that's going to give me, when I plug in 37, I do want to show you that this is very doable. 6 plus 1/12 times, again, 37 minus 36, because the whole idea is that we could do this without our calculator. So if I need to grab my calculator at this point, well, that kind of defeated the purpose. But if I go ahead and work this out, 37 minus 36 is just 1, and I get 6 plus 1/12. And I could either change that to an improper fraction, or I could go ahead and divide it by hand. Isn't going to be horrible. Because I'm being lazy right now, I'm going to go ahead and just divide in my calculator to make a comparison here. And it's 0.833333 repeating. So that's the value I get on the line. Now, just to make my point, we've got the line here and we've got the curve underneath it. Something like that. And we went right over here, and the value that we got here, that point is represented by this. The whole idea here, folks, is that this L of x is an approximation for my f of x, my actual value on the curve. So to make that point, I'm going to put a 37 into my actual function. That's the square root of x function. And because I don't know how to do the square root without a calculator, I'm going to grab my calculator and I'm going to do square root of 37. You can join me. I just got for an answer 6.0828 if I'm rounding to 4 decimal places. So that's the value on the curve right here. And I'm comparing that to the value on the line. And if I were to use my 3 decimal places that I normally round to, check that out, folks. 6.083 is what that would round to, 6.083. And those are pretty close to each other. So I'd say that method allowed me to get a lot closer. Remember where I started? I was like 6.1, 6.2, I don't know, somewhere a little over 6. That allowed me to get a lot closer than a little over 6 in terms of my approximation for the square root of 37. So we could do that for any radical, really. Now, if I was trying to do square root of 38, square root of 39, using the same linear approximation, L of x function, and just changing out that 36 with a different value, it might not be as close because we're going to be starting to get a little bit further away from my curve. But I think we'd still be pretty close with our estimate. And you could hopefully see that we could use this for something like a cube root or other functions I'm just not good at estimating in my head. Something like e to a power or natural log of something. So that's kind of where this could start to be super helpful. Just one more thing that I want to mention that we talked about briefly is that based on the concavity of my function, my square root of x function is concave down. Its second derivative, it would be negative, and I might know that, or I might just be visually making that sense of that from the graph here because I haven't actually calculated a second derivative. That means that my approximation should have been an over approximation. And we can see that in this graph here, but just make note of those two and see that that is slight over approximation there, because that's going to be something that you'll be expected to figure out. And it'll be based on the concavity of the function if we can't actually picture it. Okay, hopefully that helped just give you a little bit more of an idea of how linear approximation can be taken one step more besides just write the equation of the tangent line, use it then to estimate a value on a function by plugging into that line. Much easier to work with than the